Note card number 39, we are going to discuss concavity. You might be familiar with this word. You can think about if something is concave up or concave down. Okay, and I'm actually going to use these letters to show you what concavity is because, we're getting creative here. So if something is concave up, that means it's making kind of a bowl shape, is how we've talked about it in the past, right? So here, this would be a concave up situation, that bottom of that C there, right? It's almost like a bowl, like I can put fruit into it or water into it. That means it's concave up. It's like a smiley face facing upwards. Versus concave down, I'm gonna use a different color here. Concave down, right, is like you turned your bowl upside down, right? Things are gonna fall out of it. It is a downward shape. It looks like a hill, okay? So this is an example of being concave up. Here's an example of being concave down. Right? So my O would also have both. I have this section that is concave up, like a bowl, and then I have this section that is going down, right? This one, the N, is all concave down, right? Your C, you've got a little bit of both. So hopefully we're getting the idea here. So we're kind of looking for right side up bowls and upside down bowls, right? Or hills and valleys, okay? So that is like the basic definition, is that if something is facing this way, it is concave up. And if something is facing, this way, we've got concave down, okay? But there is also a calculus definition of concave up and concave down that we are going to talk about, make this a little bit more academic, all right? Okay, so picture we've got like a little man that's going to be running. Okay, so he's gonna be running, right? And when you start off running, you start kind of slowly, right? Before you gain that speed. So maybe after 1 second, he has run 1 foot, okay? But then he's gonna start picking up speed. So then maybe after 2 seconds, he ran 2 more feet. So he's up here. And then after 3 seconds, he's even faster, okay? So his speed is increasing. Right? He is increasing at an increasing rate. Okay? So he is running, so he was already increasing, but he's doing it faster and faster and faster, right? He's gaining speed as he goes. So if we connect this, that is what makes a graph concave up. See that concavity happening right there? We're upwards, right? So our definition of concavity or concave up is when we are increasing at an increasing rate. So write that down with me, is when we're increasing at an increasing rate. Okay, so not only are we going up, but we're getting steeper and steeper as we go. Okay, so increasing at an increasing rate is concave up. Okay, it also works the other way. Okay, if he's decreasing at a decreasing rate, so he's coming down, but at first he started decreasing quickly, okay, and then he decreases a little bit less quickly, right? So he was going really fast here, decreasing, and then it kind of slows down here. That's the other part of the concave up that makes, or that U piece, okay? So if you are increasing at an increasing rate or decreasing at a decreasing rate, that is concave up. At decreasing rate. So if he is slowing down, but he starts slowing down quickly and then more slowly, decreasing at a decreasing rate, or increasing at an increasing rate, that is what makes my concave up shape, okay, that U shape. So now let's think about the opposite situation. What if he was increasing but at a decreasing rate? What does that look like? So he is still increasing, he's making progress, he's moving forward. But at first he starts by, he's increasing really quickly, okay? But then he starts getting tired and he starts slowing down. So maybe after that same amount of time, he doesn't go as far. Right? He maybe only goes this distance because his rate is decreasing. He's getting slower. So he's still making progress. He's still running forward, but he's getting slower, right? So then after another couple of seconds, maybe he only moves this much, right? That's starting to make this curve here, right? So he is increasing still. His slope is positive. He's increasing, but it's at a decreasing rate, right? He used to be really fast. He was gaining a lot of momentum here in that first second, and then in that next second, just a little bit more, and then even less, and then even less. He's almost like stopping. He's getting so tired, right? So this one, he is increasing at a decreasing rate. Okay. Or now, what if he starts to decrease? What comes back to where he's starting, right? If he starts to decrease, but now he's like excited to get to the finish line, right? So he is going kind of slowly, but he's like, oh wait, I'm getting closer and closer to the finish line. I'm gonna run a little bit faster. I'm gonna run a little bit faster. Run a little bit faster, right? Now he is decreasing. His distance from his starting point is decreasing. He's running back home, but at an increasing rate, okay? Either of those scenarios is going to give us this upside down shape, which is your concave down. Okay, so now let's connect that to the derivative. If he is increasing at a decreasing rate, okay, what that means, the increasing means that his derivative is decreasing. So for concave down, what we're going to think about in calculus is when we're going to look for this right here. When concave down is when your derivative is decreasing. Okay. Then your concave up, this one here, your concave up then is going to be when your derivative is increasing. And now we're going to do some example problems with that. So your concave down is when your derivative is decreasing, right? His rate started to decrease. Here, the derivative is increasing. We're getting faster as we go, okay? So now looking at note card 39, okay, we are going to start talking about concavity as the second derivative because we're talking about where the derivative is increasing or decreasing, the rate of the derivative or the slope of the derivative. So that is the second derivative, okay? So this is what we just summarized here. So it is concave up if it is increasing at an increasing rate or decreasing at a decreasing rate. If f prime of x is increasing, or this is the new part here, if the second derivative is greater than 0, okay? Other one, concave down, if f of x is decreasing at an increasing rate, what we just went over, or increasing at a decreasing rate. If the derivative is decreasing, or if the second derivative is less than 0. Okay, those are all the ways to tell when something is concave up or concave down. Okay, so now we're going to try it with this problem here. So it says for the graphs of 1 and 2 below, determine the intervals where f is concave up and justify, concave down and justify. Okay, so for these problems, you want to look really carefully at what is given to you. Okay, what graph is given to you? We are being given the derivative. So I want to think about, okay, the derivative, I'm looking for concave up is when the derivative is increasing. Okay, so I want to look for all the places where this graph is increasing. So I am increasing, this is decreasing, here is increasing, and here is increasing. So I would say it is concave up from -1 to 1, and from 3 to 5, and then that justify we would say because f prime of x is increasing. Okay. So that's for part A. And then for part B, it is going down where my graph is decreasing. So decreasing would be where it has a negative slope here and where it has a negative slope here. So that is from -3 to -1 and from 1 to 3. And then the justification is because f prime of x is, you've got it, decreasing. All right. Looking at number 2, look carefully what graph is given to you. We are being given the derivative graph, or second derivative graph, I'm sorry. So we've got f double prime here, the second derivative. So in this one, I'm looking to see where it is greater than 0 is where it's concave up, and less than 0 is concave down. So greater than 0 means above the x-axis. So it's above the x-axis right here to right here, right? So for this one, it is concave up from 0 to, it crosses under at, that looks like point C, okay? Because f double prime of x is greater than 0 there, right? So that's how we know it's concave up. Then for B, concave down then would be under the x-axis, so we're going from A to 0 and also from under the x-axis from C to D. And then justify, ooh, my pen is running out of ink, sorry. F double prime of x is less than 0 there, underneath the x-axis. Last problem here is a table problem instead of a graph problem. So a continuous monotonic function, okay, so that just means that it doesn't have any breaks, any holes, anything like that, is defined for the domain of -3 to 3, so we only care about that interval, and has some values listed in the table below. Also, f prime is continuous and has only one 0. Determine the intervals for which f is concave up, concave down, and determine the x value, if any, where the concavity changes. Justify. So we are given f and f prime of x. Our definition of concavity, remember, if we look back up here, doesn't say anything about f of x. We have a definition based on f prime, so where f prime is increasing, or f double prime, okay? So if I look down here, I'm not given f double prime, so I'm going to use the f prime definition. And that definition for concave up is where it's increasing. So I want to look and see, are my f prime values growing or are they decreasing? So we're going from 0.889 to 0.75. I went down. So I was decreasing here, and then from 0.75 to 0.68, I'm decreasing, and from 0.68 to 0, I am decreasing. Okay, so I'm looking just at this bottom row here. Then from 0 to 1, I'm going from 0 to 0.68. That is increasing, increasing, getting bigger, increasing. Okay? So if I want to look for concave up, that's going to be where I am increasing. So that is everywhere from 0 all the way up to 3. Okay, so I am concave up from 0 to 3, and then we're going to justify because f prime of x is increasing. B, we want to look where it's concave down, which is where f prime of x is decreasing. So I am going from -3 to 0 because f prime of x is decreasing. Okay. Then for part C, if I'm changing from increasing to decreasing, that's where my concavity changes. So that point that I changed from increasing to decreasing, or decreasing to increasing, sorry, where we changed our direction, that's the point where the concavity changes. So we must be changing at x equals 0. So at x equals 0, because f prime of x changes from decreasing, I'm going to show you this in a second, sorry, to increasing. Okay. Where it changes from decreasing to increasing. Okay. And we're going to talk about this much more in class, but this x value, where the cavity concavity changes, that is called a point of inflection. Point of inflection. We'll talk about that much more later, but just good to front load that vocabulary so when you see it, you remember that it's linked with concavity. All right. That is it for today. Go off and take your quiz, and then have a wonderful, restful evening, and I will see you soon.